Pueden ver mi pantalla, ¿cierto? Okay, so sorry for the delay. So today we're going to move on to a new topic, which is Apache Spark. So what's the idea of the topic? Essentially, if we look at Spark versus Hadoop, what we've been learning about throughout the course, if we want to get some sense of popularity, we see that Spark is this red line here, Apache Spark. So we see some false positives here because Spark didn't exist before this date, but we see a big rise in popularity relative to Hadoop, and that Hadoop has been waning in popularity. Yeah, so Spark is becoming more and more popular relative to Hadoop. So Hadoop might be slightly underestimated because people often use MapReduce, and there are other keywords that might match with that. However, we see Spark is becoming more and more popular, and it's seen as an alternative or a successor to Hadoop. Yeah. So what is the main weakness of Hadoop? Why do we need a successor? Why doesn't Hadoop solve all of our problems? So let's see. So one of the main issues that we spoke about at the start of the course is this idea of transport costs. So how long it takes data to get from different locations where it might be stored. And here we have some referential values for the throughput, how much data we can transfer in a certain period of time, and the access or the latency, how long it takes to seek a certain piece of data from a particular location. So we see in general that the hard disks are quite a lot slower. Solid state disk or hard disks are several orders of magnitude slower to do whatever operation we want than RAM. Yeah. So based on that, what we would like to avoid is using the disk as much as possible. However, if we look at a typical MapReduce Hadoop job, we see that we have to read the data from the hard disk on HDFS. We have to write the data here to the disk. We have to read the data and write it again in order to copy it over the network. Yeah. We need to read the data here again to do a merge sort of all the batches, the sorted mini batches on each machine. And then we need to write again for the final output. Yeah, so we have to coordinate a lot of data on the disk. Yeah, so we have maybe 3 reads and 3 writes, we could say, of the data just for one task. These aspects here, these parts where we have some dashed lines, these are done in memory, but we still see that there's still quite a lot of disk IO required. Yeah. So MapReduce always coordinates between phases, such as the map, shuffle, and reduce phase, and between high-level tasks, such as counting the actors, ordering the actors by descending count. It coordinates between these things using the hard disk. Yeah. So we're always relying on the hard disk, which is in some sense a positive because it means we don't need a massive amount of memory. We don't need to store all of the data in memory. Yeah. We can use the disk. The disk is a lot larger, and we should be able to store more data in that sense. Yeah. Okay, so in every phase we have 3 coordinations with the disk, and then we need to store the data again. We need to coordinate between different Hadoop jobs using the disk. Yeah, so we have lots of disk access. This is by design. Yeah. So we saw this already counting words. If we wanted to just count the words that we saw in the very first lab, it should take about some seconds, maybe 20 seconds or 30 seconds on one machine to count them in memory. On one disk, on one machine, it took minutes. And across MapReduce, using the distributed framework, it took minutes. It's actually slower, yeah, than using the memory, for example, on one machine. This is because we have the cost of using the disk and the network. Yeah. So why do we use MapReduce then? The idea is that if we can do it in memory on one machine, perfect. Do it in memory on one machine. If you can't, use the disk. If you can't use the disk of one machine, use MapReduce. It's sort of like a last resort. Yeah. It's if we need to scale beyond what we can do on one machine. Yeah. But if you can do it in memory on one machine, that's going to be a lot faster in general. Yeah. So is there some alternative to these options that we've not mentioned? So we've seen in memory on one machine, we've seen on disk on one machine, we've seen MapReduce, which is basically on disk over several machines. In memory over several machines. Yeah. So why not maybe just use a distributed system, but not touch the disk? Just use the main memory as much as possible. Yeah. So in memory on multiple machines is the alternative that we've not considered. So if we just think about word count, for example, this running example we've been using, if the unique words fit in memory, then we could do all of this stuff in memory, right? And if we need to somehow coordinate over the network, we could send the data directly from the memory over the network, yeah? So there's no real need here for a disk if we assume we have enough memory to solve the task. And this should be way more efficient, right? Because the disk, again, is somewhat of a bottleneck in these processes. Yeah, so we have one read and we have one write, and well, we have one network access as well, one shuffle, but that's the same as in Hadoop, right? So we can save a lot of cost here. Yeah, so we just have to read the input and write the final output. Yeah, the rest of the stuff is done in memory. So this is the core idea of Apache Spark. Yeah, it's very similar framework to Hadoop, but the idea is that we can try to avoid using the disk by using memory where available. Yeah. So we're going to use the main memory. If everything fits in main memory, we'll do everything in main memory. If we're fortunate enough to have lots of machines that have lots of memory, then we can even process data at large scale using only the main memory of the machines. What if the unique words don't fit in memory? Well, we'll come back to that. But essentially, the answer is that Spark can use the disk if it doesn't fit in memory. So Apache Spark, the idea is to program with main memory. So rather than having these coordinations every time using the disk, the idea is in Spark that we can use either the disk or the memory. Yeah. So this also allows us, is quite useful to allow us to program recursively with main memory. So it means that we can access the same data over and over again because it's already loaded into memory. It will be more efficient. Yeah. So Spark storage is based on this concept of resilient distributed data set. Yeah. So in HDFS, we use the disk. In resilient distributed data sets, we have this higher level abstraction. So HDFS abstracts what machines things are on. RDDs can also abstract whether the data are in memory or in on the disk on each machine. Yeah, so it has this additional layer of abstraction. So like HDFS, RDD abstracts distribution, fault tolerance, replication, and all of this. But RDDs can also abstract the hard disk main memory and how they're used. Yep. So, okay. So in this case here, for example, this is an RDD. Yeah, this is somehow one view with different partitions of an RDD. So we have some sort of data set that we partitioned into this case 3 partitions. We can have multiple partitions per machine as well. This would be an RDD and so forth. Yeah. So if the unique words don't fit in memory, what Spark will do is it will basically start using the disk. Yeah. So if it's set appropriately, if the RDD is set appropriately, it can spill over onto the disk and use the disk. When it starts using primarily the disk, it's quite similar to Hadoop or MapReduce, as we saw. Yeah. How we program in Spark is quite different, but the overall framework, the idea is very similar. So resilient, what does resilient mean? Fault tolerant. Distributed means it's partitioned over multiple machines, and data set means a set of data. Yeah. Okay. Any questions? No. So Spark exploits a distributed setting, but it can also exploit parallelism, which means that even on one machine, it can be useful to use Spark. Why? Because we can have different partitions on one machine. And we can use one core for each partition. Yeah, so we can have multiple partitions on one machine, and we'll be processing each of those partitions. As we see here, we have 2 partitions in this machine. We can process these in parallel if we have multiple cores, for example. So in terms of the programming, how we're going to program in Spark, it's much more detailed, much more elaborate, the framework we're going to use, in the sense that rather than just have this map and reduce paradigm, we have all these things that are implemented on top of that paradigm that we can use. So we have a sort of a higher level interface. Yeah. So we're not necessarily going to be defining map and reduce functions, but we're rather going to be using some existing implementation on top of that framework. So we have all these sorts of RDDs here. We're not going to get to talk about all of them, nor are we going to be able to talk about all of the Spark programming library, for example. We're going to focus on some key RDDs, some key features. So we have RDDs for Hadoop, we have RDDs for graphs, for JSON data, for JDBC, database connectivity, Java database connectivity, I guess, to connect to a database, all sorts of stuff, right? We also have stuff for geodata, for Cassandra, which we'll see later, for Elasticsearch, and all sorts of RDDs. So specific types of RDDs permit specific operations. So the idea is there probably will be some RDD that suits what we want to do. The one we're most interested in today is the pair RDD. Now, this is the basis of a lot of MapReduce style programming. So we can implement a lot of functionality using pair RDDs already. So pair RDD is importance for MapReduce style operators. Questions or doubts? Yeah. RDD is resilient distributed data set. It's this abstraction that Spark has for a data set that's distributed across multiple machines or multiple partitions, and that can use either the disk or the memory. And resilient means that it's replicated often. So if there's a failure on one machine, it can read the data from another machine, for example. Yeah. Okay. So other questions? Good. Okay. So example, we're going to take this running example that we had before, which is this idea where we have a large TSV file where we have some information about customers, about products, about the time that the customer bought that product and for what price. Yeah. And we'd like to know the number of customers buying each premium item per hour of the day. Yeah. So how this looks in Spark is something like this. Sorry, first of all, I'm going to simplify the data a little bit so that it can be presented a little bit more neatly. So we have customers, items, hour of the day, and prices. Yeah. So we're going to start with our data in an RDD. So it could be partitioned across different machines. In this case, it happens to be partitioned by customer. It's not necessarily the case that it needs to be partitioned in this way, but we'll assume it will be partitioned by customer. So we load the data into an RDD. And here, since all these things are dashed, we assume that we can load all of the data into memory. So then we apply a filter. So we say the filter P greater than 1000. So we say that we want to filter such that we leave only those products that have a price greater than 1000. This produces another RDD. Yeah, so it transforms one RDD into another. We see here that we have an empty partition. We can call this special method called, you can see that as well, can you? Yeah. Coalesce. Coalesce will basically tell us leave just 3 partitions at most. So it basically says to reduce multiple partitions into a smaller number of partitions. So if we know we have 3 machines, maybe we'll say, okay, give me 3 partitions, 1 for each machine. Well, moving on to the next slide, where I need to move this again. Where will I put it? Here? Yeah. So we apply a distinct because we only want to count each product per customer once. So we apply per hour of the day. So we apply a distinct. This gets rid of all the duplicate tuples in the RDD. As we see here, we have 2 duplicate tuples. We get rid of 1. We call map IH, which is item and hour, because we want to somehow group by item and hour. And we're going to output a 1 for each key, as we see in MapReduce, because we want to count these things. And then we apply reduce by key to sum all of the values for each key, the keys here being items and hours. And this will give us the number of times each pair appears of item and hour. So we know how many times that item was bought in that hour. Yeah. So there are some details here that are straightforward, like distinct. There are some details like this map and reduce by key thing that look a bit weird, that we'll have to talk about in a little bit more detail later. Yeah. So this is the overall idea. And then finally, we can save. Yeah. And this save transformation, or this save operation, I've indicated in a weird color, in a different color to all the rest, because it's different from all of the other steps. And I'll have to explain why that is different. Yeah. So we take our RDD and then we can save it to whatever we want. In this case, we assume we save it to HDFS. Okay, so this is a sort of a taste or a flavor of what we can do. Is we see this is a bit more high level than MapReduce. We have functions like distinct, and we have functions like map and map is also MapReduce, reduce by key. We have some higher level functions. Yeah. So we'll have to talk about some of these, and we'll have to also talk about what is the difference, why these things are in different colors here. Okay. So any questions? There are multiple questions I still have to answer here, but if there's any questions. Yep. What is it? The sigma. Yeah. So the idea of the sigma in reduce by key, we're going to have to pass a function to reduce by key. And this is just a little abbreviation to say that reduce by key, what it will do is for every key, apply a function over all the values for that key. So what this says is for every key, sum all of its values. Yeah, just it means sum. Yeah, we'll see that in more detail soon. We good? Okay, so in Spark, we then have two notions, transformations and actions. And these are the two different types of steps we saw earlier. So transformations are run lazily, which means that we're going to try to not run them for as long as possible. Yeah. They result in virtual RDDs. These are not actual physical RDDs, nor in memory, nor on the disk. They are only run to complete an action. Yeah. So we're not going to run them until we actually need to complete an action. So if we take these steps where we load the data, we filter them, we apply a coalesce, none of this stuff is done. Yeah, we don't do any of this yet. So these are just sort of steps that we add to, or we'll see later, to the directed acyclical graph. But essentially, this is we're building up the steps that we want to process, but we're going to try to delay these things as much as possible, because often we can combine them. We can combine multiple steps into one. We can optimize these processes. Yeah. So in terms of the transformations, there's a long list of transformations in Spark. It wouldn't be possible to talk about all of them, but I'll talk about some of the most common ones here. And some of them are straightforward, and some of them are going to require more explanation. And some of those that are going to require more explanation would be group by key, reduce by key, aggregate by key, and these are super important. So I'll talk about them a little bit later. So what do we have here? What do we have here? We have an RDD. So this is some data set, and then we can use dot and the name of a transformation like map or flat map filter. We have some different types of arguments here. If the argument is f, it means that it's a function argument. So we're going to pass a function. Yeah. So it's sort of functional programming style. Yeah. If it's a dot, it just means it's some sort of scalar or number or string or Boolean or something like that. Yeah. So here we see some of the transformations are underlined. Any guesses why some of these might be underlined without me explaining what these transformations are doing? Anything particular about the underlined ones versus the non-underlined ones? So for example, why would union not be underlined, but intersection is? Yeah. So the answer is that these transformations, any ideas? They cannot be processed tuple at a time. They require comparing more than one input line or input tuple. Yeah. So this means that we need to somehow coordinate the data to make sure the tuples we need are gathered together. In all of the other cases, we can process them kind of tuple by tuple. Yeah, just line by line. We don't need to have access to other tuples. In the case of union, we can just take if there's 5 partitions in R and 3 partitions in S, we can just say R union S is just the 8 partitions. We can do it virtually. Yeah. So we don't need to do any particular coordination. Yeah. So these require shuffle. It means that we're going to have to localize the tuples that are needed together to be compared or distincted or joined or whatever. We're going to need to partition them in a particular way and shuffle them. Shuffle means potentially send the data over the network. Yeah. So the transformations we have a list of a bunch of transformations here. So the first one is map. So for every input value, we're going to output one value. Yeah. So this is sort of like a projection or a transformation line by line of the output. Yeah. So if we have n lines in the input, we'll still have n lines in the output RDD. So for example, given A, B, C, we can just project A and C. Yeah. So in a lambda sort of calculus, this is our function, and our function takes an input tuple ABC and it outputs AC, nothing more. Flat map is different in that from a single input tuple, it can output 0 or many tuples. Yeah. So this would be useful, for example, if we wanted to count the number of words in a file where our input tuple was a line, then each line would be exploded into several output values. Yeah. So here we have an example where we write from ABC, we write AB, AC. We write two tuples from one. Filter. So filter allows us to apply a selection on the RDD. Yeah, so it means that we can apply a criterion or some criteria in order to filter and leave only the tuples that satisfy that criteria. For example, the function in this case would be A greater than B. Yeah, some condition that returns a true or false value. Map partitions allows us to map all of the elements of OR to the output, calling F once per partition. So basically what it allows us to do is call a function that will take an entire partition and then give us an RDD over that. Yeah, so it will produce some sort of, it's some function that will take a partition or an RDD, a list of tuples as input and produce a potentially zero many tuples as output. Yeah. So it's a partition level function, not a tuple by tuple function. Map partitions with index is quite similar, but we can also get the index of the partition as an input. Yeah, so we can know, is this the first partition? Is this the second partition? What partition are we working with? Which is actually, I don't know why that's so frequently used. I don't really see a big use case for that, but okay. Sample, we can take from a sample from the RDD, we can take a sample which has 3 arguments with replacement, fraction, and seed. Yeah. So with replacement, do you know what sampling with and without replacement means? No. So if I take a sample of something, let's say I have 3 objects. Okay. 3 different objects. I have 3 objects. No. I have 3 objects. If I want to do a sample with replacement, the first thing is I take my sample. Yeah, that's one element. If I do with replacement, I put it back in before I sample again. So I could potentially sample black twice, the same thing twice. Yeah. If I do without replacement, I sample this, but I'm not going to consider that again in the sample and in the next sample I take. Yeah. So if I want to sample 2 of these 3 elements with replacement, I could sample the same thing twice. Without replacement, they have to be 2 distinct values. Yeah. So this is with and without replacement. Then we have the fraction, which would be like 0.1 would mean a 10% sample. And we have the seed, which is just a random seed used for the pseudo random selection. So if we pass the same seed, we would get the same random or pseudo random sample. Okay. So we have some relational or set type operators. In this case, we have union, which will just take all of the tuples that are in or S. We'll take the intersection, which are all the tuples in both or and S in their intersection. And we can apply a distinct to remove duplicates from an RDD. Okay. So the ones that are a bit more interesting, maybe a bit different, are group by key, reduce by key, and aggregate by key. Yeah. So group by key allows us to basically group all the values by key. So basically, given some key, it will group all of the values in the RDD associated with that key. It doesn't do anything to that group. It just groups them. Yeah. A bit like in Pig, where you call group by and it just groups them and you can access the bag of tuples associated with that key. Reduce by key allows us to define a function that will apply over the group. Yeah, so it groups by key and then it applies this function over all the values with the same key in a particular group. So this function might be, for example, to sum all the values of the group. So we define it over a pair of values, but it will be applied in sequence over all of the values of the group. So in this case, the sum. Aggregate by key is a more complex function that allows us to do, this is essentially MapReduce. This is the generic MapReduce style function. So for aggregate by key, it allows us to define a 0 value. So C is an initial value. It allows us to define a combiner function, and it allows us to define a reducer function. So we'll have to see an example of how these work later. Yeah. So combiner is like a mini reduce, and then we apply a final reduce to get the final output. I'll have to explain to you how that works with an example. We have sort by key, which is pretty straightforward. It allows us to order by whatever the key is we've defined. We have join, which allows us to join OR and S by their key. Yeah. And we have co-group, which allows us to group the values by key in OR and S together. So I have E here. So I guess I translated this from Spanish at some point, but anyways, by key in OR and S together. So yeah, I teach a version of this in Spanish for Diplomado. So co-group is essentially doing the union of or and s and then group. Should be equivalent to that. One thing I didn't mention, by the way, I think, apologies, is that all these transformations are defined for pair ORDDs. These ones here, sorry. These transformations here require a pair ORDD. As you see, they say key and value and so forth. So we need a pair ORDD because a pair ORDD defines keys and values for every tuple. Yeah. So a pair of a key and a value. So all these elements here require a definition, an explicit definition of what is the key of the tuple in the ORDD to already be given. Then we have Cartesian product, which allows to apply the Cartesian product of or and s. Use carefully, please. Or pipe C, which allows us to create a pipe from standard in. So this allows us to do some hacking where we can process data in an ORDD using command line arguments like grep or awk or perl or whatever we would like. And the result then is an ORDD with the output of the pipe. We can apply coalesce, which we've seen, which will merge various partitions into at most n partitions. And we can repartition if we want. So coalesce doesn't repartition, it just tries to keep the data locally and merge them into at most n partitions. And then we have repartition, which will try to rebalance everything. So this is common. Maybe it might be a good idea if we've applied a lot of processing. We might have an unequal distribution of data in our output. If we apply a certain type of filter, we might end up with a lot of data in one partition and little data in another partition. So before going further, it might make sense to repartition the data before we go. So I have to explain in more detail the difference between these things here, these three functions, which I'll come back to. But any other questions for now? Yep. I'm not sure. When would you want to do that? That's a good question. I don't know, maybe if there's, I mean, I could imagine cases, but I don't know in data processing. If you have a lottery, for example, and somebody wins the lottery once, that's a random sample. But if they win it again, congratulations to them. I don't know. I mean, I think without replacement makes more sense. If there's some sort of methodology that requires with replacement or when you would do that. Yeah, I don't know. I don't know. I'd have to think about it. This is society. I would say, yeah, I would say, okay, so with repartition in particular, if you know that you're applying a filter that's selective, which means that it's going to remove a high percentage of your data. And if you know maybe that, okay, it's not going to apply equally to all partitions because of some load balancing issue, then you would know that after this filter that your ORDD is going to be unbalanced. Yeah, or it could be unbalanced, right? So you could know that on one machine, there could be a lot of data and on another machine, very little. So repartition is basically just this way of saying, please partition things equally to make sure load is balanced before the next processing step. Now, I would say in most cases, these are not necessary. I wouldn't say these are common that you need to use these, but they may be very useful in certain cases where there's performance issues because of load balancing. So you could add this into your script. You could maybe debug your process and realize, oh, this is because this filter just seems to be processing or seems to be leaving a lot of data on this one machine for these values. So you could do that way. Another way could be if you know that your partition is tiny, you know that like you're going to be filtering 99.9999% of the data, you could call coalesce or repartition with 1 to essentially just end up with one partition because it's not worth distributing the data anymore, for example. Yeah. More questions or doubts? Okay. So we've seen transformations. We've seen a lot of transformations, and there are more. Again, I'm not going to present all of the transformations, just the most common ones. We also have actions. So actions are where things execute. Now, this is where Spark actually starts to do some work. Yeah. So until now, we were not going to do anything. And then at the moment of calling an action, we're going to execute. So these result in real materialized ODDs that could be on the disk or in main memory. Yeah. All ancestor transformations are run, all of the things that the action depends on. So for example, here, if we call save, now we have some verifiable observable output, which means that we need to call all of the transformations in order to yield that observable output. Yeah, so some external thing can now see some results, which means that we need to run all of these transformations. Okay, so all steps are now run. It's important to note here that the RDDs are not kept. Yeah, these intermediate RDDs, these dash things here, they're really just temporary references to an RDD. Yeah, they're like variables. They don't really exist. So it's possible, for example, if we have a sequence of 3 filters, filter price less than 1,000, filter hour greater than 10, filter client, whatever, that we could actually combine all of those things into one filter with and, filter price and customer and then there's these RDDs don't exist, yeah, these intermediate ones. So these are RDDs here are not actually going to be RDDs, are more like references to phantom RDDs. Yeah, they're not going to be materialized. So these RDDs are not kept, and this is important to remember for a reason we'll see in 1 second. Yeah. So what are the actions? The actions are as follows. Some of the common actions. Typically, we have things like save. We have some sort of output value. So we take some sample or we read some output to our laptop or notebook. You can see some more actions here. To go through some briefly. So we have a reduce action. Again, we see some Spanish, sorry. So we have a reduce action where we apply a function on the RDD in order to reduce all of the data of the RDD to one value. This is not reduced by key, which does it by key. This is sum the entire column of values into one value. Yeah, so it's like a sum without a group by in SQL. Of course, the reduce can be any function. Yeah. We have collect, which loads some our data or into the local application. So maybe we get the top 100, which we're interested in. We apply all the counting and pairs and co-stars and so forth. We get the top 100, and then we say, okay, give me the top 100 into my Python application so I can do some more analysis or whatever. Yeah. So we can apply a count to count the number of tuples in the RDD. We can get the first tuple of OR if we want to get a flavor of what that looks like, or maybe just get the top value. We can take the first n values into the local application. We can take a sample of values into our local application, again with replacement number and seed. We can save our RDD as a text file, as a sequence file, or as an object file. So a text file just means plain text. This is probably the recommended. I like plain text. Plain text is nice. I can read it from other things. I can use awk or grep or sed or whatever to see what's in there. So that's what I would typically use. But if we really want to optimize something, we could also save as a sequence file, which is this binary format used by Hadoop. You'll have to use Hadoop to read it. Or you can save it as an object file, which will use the native Java serialization, where we'll also keep all of the types and stuff. So in the third lab, when you read the output of another Hadoop job, you had to parse it again and figure out what were the types, and this was the string and this was the int. If you use serialization, you don't have to do that. It will automatically recognize what the types were. But in general, I like text files. I can see what's going on. But maybe if we wanted to optimize some process that we're going to run frequently, we could think of maybe a sequence file, maybe an object file for some other use cases. So we have count by key, which returns the values for each key, returning the answer locally. So this means basically that if we had done some big group by key or something, and then later we wanted to do the count of how many values there are for each key, and we wanted that on our notebook, we can call count by key. We can call for each f, where we apply a function over every element of the RDD, typically to interact with something external. For example, if we wanted to save every value in the database, or we wanted to print it to an external, to a system out. Yep. So what these have in common, all of these actions these are just things that have some external results. Yeah, some other application is going to receive the output. There's going to be a save file somewhere. or there's going to be some sort of external action outside of Spark. So this is why there are actions, and this is why these, at the moment of calling an action, we trigger all of the transformations that action depends on. Any questions or doubts? Of course, we need to be a little bit careful if we, for example, call collect on a massive massive RDD that's been distributed across thousands of machines, and I call collect on my machine here. That could cause trouble, but we can also use take or whatever else we would like to use for that. Okay, so if there's no questions, we can get to the transformations for pair RDDs in a little bit more detail. And I said that I would explain to you in more detail what these three functions are doing. Understanding these three functions as well will be critical for the lab on Wednesday. And they're very common functions that we want to apply because they allow us to do map reduce style processing. So we have group by key, we have reduce by key, and we have aggregate by key. Yeah. So group by key accepts no function. Why not? Because all it does is take a key and group all of its values into a bag of values for that key. It applies no aggregation, no function over those values. Reduce by key groups by key and then applies a function over all of the values associated with each key. For example, to sum those values. Aggregate by key has three values. It has a 0th value, a combiner, which is used to initially group values within a given partition, and then a reduce function, which is used to combine the intermediate values from each partition. So I'll have to explain how these are different with some examples, because probably still doesn't make a whole lot of sense. Let's say we wanted to sum all values for each key in OR. So what are the keys in OR? Again, OR is a pair RDD, so by definition, it has already had its key defined. So in order to sum all values for each key in OR, we could try to use group by key. Yeah. If we use group by key, then we have our RDD here. We group by the key, and then we get tuples like this, where we have a key and we have a bunch of values associated with that key. Yeah. So we group by key, we get something like this. So then we apply a map so that for every key and group of values, we apply some function. So we apply in this case that we take K and all of its values, and we output K and the sum of all of its values. Yeah. So this is group by key. So we can always do it this way. We can group by key, and then we define our own function over each group using a map. Reduce by key, groups by key, and then applies this function over all the values. Yeah. So have you seen lambdas? Lambda syntax in Java and Python and Scala? Have you seen Scala? Some of you have seen Scala. I think this is new. I don't think people have arrived to this course knowing Scala before. Spark has been implemented in Scala. So yeah, so we could look into that. Okay, so this is a lambda syntax. Yeah, it's an abstract lambda syntax. So what it's going to do is it will take the first value and the second value associated with the key and sum them together. Yeah, so it defines how to combine pairs of values, and that's used to combine all the values associated with a given key. The aggregate by key function, what we have is a 0 value. This is our initial value. So we just define this as 0. Yeah. We have here we're defining the sum in the combiner, so the combiner can sum the values together, and then the reducer can sum the values produced by the combiner at the level of each partition. So in this case, which is best? So 2 uses a combiner, 3 does exactly the same as 2, but is less concise, so 2 is best. So essentially here, aggregate by key, when we use the same combiner and reducer, it would often, or it always makes sense to just say reduce by key. Reduce by key is sort of like a shortcut for this aggregate by key here, where we have the same reducer and combiner. Yeah. So let's look at an example where we don't want to use reduce by key. We rather want to use aggregate by key. So let's say we wanted to take the average of all of the values for each key in OR. Yeah. So the average is different because it's not commutative and associative. Yeah. So we can't just take averages of some of the intermediate values and then average those intermediate values. Yeah. So if we take 6, 12, and 18, yeah, We take the average of 6, 12, and 18 is 12. Yeah. If we take 6 and 12 and average it first, it gives 9. If we average that then with 18, gives us 15, I guess. No. What does it give us? 9 and 18, 27 divided by 2, 13.5. Doesn't give us 12. Yeah. So we can't just average bits and pieces of the data and then take those averages of the intermediate values. Yeah. So to average all of the values for each key in OR, let's have a look and see what we can do. The basic way to do it is to just do a group by key. Yeah. And this will produce for each key all the list of values associated with it. And then we apply a map to transform a key and its list of values into a key and the average of those values. Yeah. So we can do this. No, not too bad. It looks quite okay. If we wanted to do a reduce by key, we can't just say UV maps to U plus V over 2. Yeah, we can't take the average of U and V. Yeah, because of the reason I just said. If we take the average of 2 values and then average that with the next value, it's going to distort the average. It's not going to be the correct average. So what we can do to take the average using reduce by key, we can't do it directly. It's not possible. What we can do is we can use reduce by key to get the sum. We'll, by another process, get a count. We'll join the sum and the count, and then we'll divide the sum by the count. Yeah. So this is quite a difficult roundabout way to process this. So in the reduce by key here in OR1, what we're doing is we're storing the sum of the values for each key. In OR2, we're going to count the values for each key. How do we count the values? We map each key and value to key and 1, and then we sum the ones for each key. Yeah. And then in OR3, we're going to join the sum and the count, and we're going to map from a key with a sum and a count. We're going to output sum divided by count, which is the average. Yeah. So this is not so straightforward. So how could we do this maybe with aggregate by key? Could it possibly look a little bit neater? So here's our aggregate by key function. It's not all that much shorter, but what we have is a 0. We have to define a 0 value, and here we have 2 zeros. Why do we have 2 zeros here? Sum and the count. Yeah, we're going to maintain the sum and the count as a tuple of 2 integers. Yeah. So first we need to define our combiner, which says that given a raw value in the data and a current sum and count, how do we update our value or sum and count? Yeah. So we have sum, count, yeah, and a value here. So we update this by adding the value to sum and adding 1 to count. Does that make sense? Yeah, so we're accumulating our data about the sums and counts. In our reducer, we then need to say how to combine 2 values that are produced by the combiner. Yeah, these will come from the different partitions. So we're going to apply this function at the level of each partition, and that's going to produce a sum and a count from each partition. And then we need to say how to combine multiple such values coming from different partitions. So we have 1 sum and count here. We have another sum and count here. How do we combine them into a final value? We sum the sums and we sum the counts. Yeah. And that should give us the final sum and count. Yeah. In our final step, we still have for each key the sum and the count. So to get the average, we need to apply this map transformation. Yeah. So we need to take the key with the sum and the count, and we need to map it to key sum divided by count. We have our average. Yep. So I'll go into that in a little bit more detail. It's quite critical to understand what aggregate by key does. So which is best here? 3 is best for a very particular reason, which is that 3 has a combiner. We saw this notion of a combiner that can reduce the data before it sends it over the network. So we can reduce all of the data in a partition into one per each key. All of the data in one partition, we can per each key reduce it to 1 sum and 1 count. Yeah, using the aggregate by key, something we cannot do in the group by key. And it's only one operation. We don't need to apply 2 different operations and then a join. Yeah, we don't have these 3 underlined operations that cause shuffles. So we have one operation with a shuffle, we have a combiner. So 3 will be by far the most efficient in this case. Yeah. It'll be particularly more efficient than 1 if we have a lot of values per key, and they tend to appear in the same partition. But okay. So 3 is let's say the correct way or the best way to implement something like an average or a non-commutative, non-associative operation over the values. Okay, so we'll go through it in a little bit more detail to see what it looks like in terms of the processing and when the functions are applied and so forth, to make sure it's clear. It's sort of an important concept that causes confusion. So the first thing we're going to do with aggregate by key as part of the framework is group all of the data by key. Yeah, so we're going to take all of the keys here, P1 and P2, 25 and 30. Yeah, so we're just grouping for each partition here. For each key, we're grouping its values. Again, in this ORDD, it has to be a pair ORDD, so we have to define a key. So we group all of the values for each key. And what we want to do again is compute the average eventually. So we're going to first, for each partition here, we're going to apply the first function, the combiner function, over each partition. So this will give us for each partition the key and a sum and a count, yeah, by applying this operation here. So for every key and every partition, we end up with a sum and a count as a result. Then we do our shuffle, and we're going to bring together all of the pairs associated with each key from the combiner. So here we have P1, and we have a list of sums and counts from different partitions. And then we apply our reduce function here in order to create our final output. Yeah, so, or not our final output because we have to take the average, but our final sums and counts. So here we sum the sums. So 30 plus 10 plus 20 is 60. 1 plus 1 plus 2 is 4. This gives us the final sums and counts. And we can take the average then. Yeah. So we divide the sum by the count and gives us our final average. So we see there's one shuffle, we see there's a combiner. So we managed to reduce a lot of the data associated with each key within each partition. So this is a pretty efficient way to do things. Yeah, so again, this green function, this first function here is applied on the site prior to the shuffle. And the rest here is applied after the shuffle. So if we look in more detail at how this process is applied. So here we have, for P1, we have the value 30. And P1, we have the pair with the sum 30 and the number 1. 0, 0 is the default value is the question. It's a 0. Actually, we can define it here. It's sort of like, what's your base value for your operation? So if you were doing a sum, it could be 0, for example. If you wanted to, for some reason, multiply all of the values, you could define it to be 1. So it's like your base value. Actually, we'll see it here to show in more detail. So your first value here is you start with 0, 0 in your combiner. Yeah, this is like your initialized sum and count, or your initial value. Yeah. So then for your first value is going to be, in this case, for example, 30. So you take 0, 0, 0 here, you take 30, and then you update these values here. So 30 plus 0 is 30, and 0 plus 1 is 1. So that gives you the score of 30 and 1 here. Yeah, so 0, 0, 30, and then it updates for 31. In the case of 25 and 30, so you start with 0, 0, 0, you have 25. So then you get 25 and 1 as before. You add 25 to 0 and 1 to 0. And then you take 25 and 1 as your next value, and you take 30 here. So then you add 25 and 30, you get 55, and you get 2. Is this clear? So we use this 0 value to combine the first value that we're going to find. Yeah, so we need to somehow initialize or define our initial value for sum and count here. It doesn't have to be 0. It could be whatever we want to define it as. Okay, so that's that process here. If we look at this process here, it's quite similar. So in this case, we define the function as between pairs of pairs that will write our final pair out of sum and count. Yeah. So we need to define how to combine pairs of values that were produced by the combiner. So in this case, we have the pairs 30 and 1, 10 and 1, and 20 and 2. So we start with our 0, 0, 0, 31, and we produce 31. And then 31, we combine with 10, 1 to produce 42, and then 42 and 22, we combine to produce 64. Yep. And so forth. Any questions or doubts? Well, all good? Okay, so we understand that. Yeah, so when to use aggregate by key and when to use reduce by key. If you find that you're defining the same combiner and reducer, probably you can just use reduce by key. It will be more straightforward. Otherwise, if your operation is not commutative or associative, if you need a different combiner and reducer, probably aggregate by key is much better. Yeah. If you don't really need a combiner, then if it doesn't benefit you in any way, then group by key could be the way to go. So you group by key and then map to apply a transformation in the groups. Okay, so no questions or doubts? Okay, so a key aspect in terms of the processing of Spark jobs is how the execution is run. So there's this notion of a directed acyclical graph where we're going to have RDDs that are transformed into other RDDs, and that forms a graph that has no cycles. Yeah. If it had cycles, then we'd have a problem with dependency, what we would run first. So if we return to our example that we've seen before, the number of customers buying each premium item per hour of the day, we could represent this in Spark as a directed acyclical graph, where we're going to start by applying a load transformation to load an RDD. Then we're going to filter that RDD to produce another RDD. Then we're going to coalesce that RDD to produce another RDD. Then apply distinct to produce another RDD, to map to produce another RDD, to transform each line into another line, and then apply an action count or by RDD count by key to produce a final RDD. Yeah. So here, this RDD is materialized, and these are only references to RDDs. Yeah, they're not actually materialized at any point. So this is one RDD. Let's have a look at a more interesting branching one where we have some information about customers. And now we want to know not just the number of customers buying each premium item per hour of the day, but also the number of female customers older than 30 buying each premium item per hour of the day for some marketing purposes. So in this case, now we have some information about customers and we load that from a different text file. So now we're interested in applying the same process, but only considering the customers that are in this RDD here that are filtered. So we loaded the data and filtered to the customers we're interested in. And we assume that this RDD here contains those customers. So what could we do? We can join these RDDs here before we start applying the map and count by key. We can join the two RDDs here. And then we can apply a map and count by key here in this case, and we can produce a second count, which gives us the information about certain customers that we're interested in. Yeah. How does this work? Well, we can do this, no problem. We have a directed acyclical graph. We have no cycles, but there is a problem here. Anyone see what the problem might be? So let's assume we call this count by key first, yeah? And then later we call this count by key. What happens when we call the second count by key, where we do an analysis for specific customers? So what will this count by key trigger? It will trigger this map. It will trigger this join. It will trigger this filter, this load. Yeah. But also, it will need this RDD, which is not material. It's never materialized. So it's sort of an intermediate step. Yeah. So the second count by key here will also trigger all of this stuff here that we already did on receipts. Yeah. Because that RDD, this RDD here that we're referencing doesn't exist. To produce that RDD, we have to produce all of these steps along the way. Yeah. So our problem is that we're duplicating a process, a lot of work here that we don't need to duplicate. So how do we avoid this? Well, Spark provides us a solution for that. And that solution is to cache an RDD. Yeah. So if we see in our directed acyclical graph that we have an RDD that has an in degree of more than 2, an out degree, let's say, that's used twice. Yeah, like this, that has an out degree of 2 or more. then we should consider caching it. If it's going to be used twice or more, we should consider caching it, unless it's already a material RDD. Yeah. So if it's some output of a transformation, it's not going to be materialized. Yeah. So in that sort of case, unless it's very cheap to produce every time for some reason, we should consider caching it. And this caching the RDD produces a materialized RDD. It actually writes it into some memory or disk or whatever the RDD is configured to, right? So you can use it multiple times without having to recalculate that every time. So this allows us to do also recursive types of processes in Spark. So this is cache. Cache is nothing more than materialize this RDD, so we can use it multiple times without having to recompute it. So this is called cache, or sometimes persist. Cache is still lazy, right? So it still won't run anything because there's no external action on cache. That's like, well, I mean, it has to store it to some memory somewhere, but it's still internal to Spark. Yeah, it's still in some Spark RDD in memory or on disk. So it still needs an action to run. We can use memory for this, or we can use disk for this, or we can use a mix of both. We can use memory, and if needs be disk, whatever it might be. Default is memory only. So if you're using cache and you run into memory problems, it might be because of that, because it's trying to force everything into RAM. Okay, questions about cache? Persist? All good. Okay. So in the kind of Spark lifecycle, as it's called, what we have are some input RDDs that could be loaded from HDFS or some other source, a database, a NoSQL store, whatever it might be. We transform those RDDs, and then we can use cache or persist to reuse RDDs several times, ones produced by transform that are not material, and then perform some action, which causes some external sort of results that we can observe. So we can output to a file, the database, a local terminal. So this is essentially Spark in a nutshell, the core of Spark. So beyond the core of Spark, we have a bunch of other aspects or components of Spark. So we have in Hadoop, we have MapReduce framework, which is used for processing data at large scale. In Spark, we have the Spark core, which is what we've seen with RDDs. We have Yarn, which is yet another resource manager, which I haven't mentioned, but it's more in the administration of Hadoop. It's used to allocate machines and resources to a particular task, to say what machines are free, whether there are resources available to run a task or not. That's equivalent is Mesos in Spark. Spark can also use HDFS, or it can use an internal abstraction of data called Tachyon, which you don't know so much about. And another interesting thing is that we have something similar to Hive or to Pig with Spark SQL and data frames, which we won't get into because it's kind of similar to what you've seen before. We have things for machine learning, we have things for streaming, we have things for processing graphs, there are libraries for geographic data. There's a whole ecosphere of things around Spark for different types of scenarios. Yeah. So all of these, of course, the first step in understanding all these is to look into Spark Core. We're not going to be able to get into everything that's here. Some of them we'll see in different iterations. We'll look at graph processing a little bit later in the course, but in the context of Giraffe. But there's a very extensive set of libraries for specific types of domains that somehow build on top of the core of Spark that we saw today. Any questions or doubts about that? Okay, so returning to Spark versus Hadoop. So it's important to mention that Spark in some sense can be seen as making Hadoop obsolete, because it should in theory be able to do everything that Hadoop does. Yeah, in the sense that you can configure Spark to use the disk, and you can tell it to only use the disk if you have some sort of task where you don't want to use a bunch of memory for that. Also, Spark claims to be super fast at sorting data, right? There are these penny sort benchmarks and all these competitions for how quickly you can sort data, because this is the core of a lot of large-scale data processing. Indexing and so forth requires sorts, efficient sorts, and massive amounts of data. So Spark in general claims to be super efficient just for sorting, yeah, using disks, for example. But that's according to Spark. So In my own experience, Hadoop is more reliable. Sometimes it's difficult to configure Spark. You'll get out of memory exceptions. If it's a sort of thing that, you know, it's configured well, I'm sure it would be a lot faster to use if you have clusters with a lot of memory. But often I'll just use Hadoop because I know it will run unless my code is buggy or something. It will run and finish at some point. Yeah. Whereas with Spark, I've just seen that configuring it is a lot more complex. You get out of memory exceptions sometimes and you don't know why and so forth, but okay. So Spark in general has become a lot more popular than Hadoop. So why do we speak about Hadoop then? Well, I think Hadoop is a important first step. It's still widely used, first of all. You can see it's sort of plateaued here, but it's still commonly used. And it's an important first step to understand also Spark. Why Spark came to be and how Spark operates. So Spark is heavily inspired by Hadoop, but with this idea of better exploiting main memory of machines in a distributed setting when available. Yeah, so that's Spark. Any questions or doubts? Okay, so on Wednesday we're going to have the lab, which will be on Spark. We'll give you some similar tasks. You're going to look at this time a TV series, I think, and you're going to do some analysis of top TV series in Spark. Spark has 3 options. It has Java, Scala, and Python. Python is not really ideal, but you can use it. There's PySpark. There's a library that interprets Python as Spark tasks. It's not, again, it has a cost. If you like using Python, that's fine, but the Python functions, if you pass functions to this, they will be called in Python, and they're likely to be less efficient. Yeah, so it's interpreted again. So Scala and Java are pretty much the same because Spark was implemented in Scala. It runs in the JVM, so there's really no difference between using Scala and Java. Yeah, but Python, it needs to do some magic in order to get PySpark to run. But at least it's first party. Yeah, so it's actually provided by the Spark people. It doesn't implement everything either. Sometimes some things are not implemented. Yeah, so that's it. We'll start with the projects as well. So in the forum, I'll start a thread, and you can start to propose your names for groups. If you don't have a group, don't worry. If you have a group of 2, that's fine. You can propose a group of 2 and we'll add somebody else. We will get to groups of at least 3 in all cases though. Yeah. So in case there are some extra people, it's not divisible by 3. We have mod 3 equals 1 or 2, then we'll have some groups of 4, but only in that case. So please don't propose groups of 4. They're not allowed. Okay, that's it. Any questions, doubts? Okay, see you on Wednesday. Any doubts in the Zoom? Nope. Okay, see you guys.